Let us start the lecture. Today's lecture is going to be only 1 hour, okay? I have another commitment that I couldn't cancel it. So 1 hour, but there is no break, obviously. Okay, so 1 hour, no break. So what we're going to do today is that, as you noticed, we found out the matrix representation of a linear operator. Everybody understood that. The good news is that I give you the homework, the first homework, by tomorrow. So over the weekend, you can solve that. It's a long weekend, right? Is that true? It's a long weekend. So you have enough time to solve the problem, and you can submit that 1 week from today, from tomorrow, okay? Actually, from today, because I collected on Thursday here, okay? And the company side students, the video streaming section, I asked them to send it to a TA who is basically correcting those homework, and then send it back to them directly with the email attachment. So so let's start. I'm going to communicate that again by Blackboard about the homework and what you should do and so forth. But I just wanted to let you know. We found out that this process of matrix representation of linear operators helps you to find some other transformation. One of them, for example, let's say the one that basically we use a lot is the same thing. Instead of counterclockwise 90 degree, let us refresh your memory from last time and solve the problem when there is an arbitrary angle. Okay? So let us do the following. This is another example that shows you rotation counterclockwise let's say alpha degree in a geometric plane. Around the origin. As you know, when I say around the origin, later on we find out that this origin could be the z-axis for a three-dimensional case. So it's the same type of situation. So we will learn about 3 types of transformation for around the x-axis, around the y-axis, around the z-axis, later on, when we talk about the kinematic of robotic manipulators. Okay, so we'll talk about that later. But for now, let us consider to see what we can take advantage of this linear mapping. So I have this geometric plane. So I put this 2 vector as a basis vector, but I call this one x1 and x2. And usually you can consider the length of these vectors to be an arbitrary length, but we can put it usually as a unity. That means we are normalizing it so that when you do operations, it's going to be easier. So you don't have to consider the magnitude as well. So what happens is that now we want to move this x about alpha degree, let's say, right here. So x1 goes to y1. Everybody understands, right? So the x2 alpha degree goes to this point. So x2 goes to y2, x1 goes to y1. So now we have to find out what is, we know that y1 is the same as L operating on x1, right? Exactly what we did last time for the 90 degree counterclockwise. Now we do the following. y1 is equal to L operating on x1, and y1, now it's rotated alpha degree with respect to x1 and x2 that are the basis vector here. We find that the first column of the matrix A, okay? The first column. So in order to do that, you do the projection here. So the x component of that one becomes cosine of alpha, and the other one becomes what? Sine alpha. Everybody can see that, right? So the cosine alpha becomes this component, and the sine alpha becomes this component. Is that clear? Now we go to the y2. y2 is equal L operating on x2. With respect to x1 and x2, you have this the second column of the matrix A. How do we do that? We do the projection here and here. If this is alpha, this becomes minus sine alpha. And the cosine alpha. Everybody can see that. So that's minus sine alpha, and this is the cosine alpha. So this becomes the first columns of the matrix A. This becomes the second column of the matrix A. So you can immediately write the matrix representation of this linear operator is equal to cosine alpha, here sine alpha. This is minus sine alpha and the cosine alpha. Is that clear? Okay. So now you understood the matrix representation of linear operator. I mentioned last time that there are several situations that you might consider the equation of beta is equal A alpha that we talked about. From the application point of view, we also said that the equation AX equal to B can resembles the same situations as A alpha is equal beta. Now, I expect that all of you should go there and investigate the solution of these algebraic equations, whether it's a square, tall matrix, or fat matrix. Did I talk about that at all? A little bit. Did I talk about the minimum norm solution? Yes? Okay, so I would expect that you just consider these equations, and then when B is element of range space of A, you know that there is a solution, and the solution for this matrix depends on the three cases. As I mentioned, case one, when this is, let's say, a square case. In that case, X becomes A inverse times B. Analytically, you can find that one or any other method. Case two, it was the situation that you have a fat matrix like this, right? And then we said that if this matrix A is a fat matrix, we know that most of the situation B is an element of the range space of A automatically. So in that case, the solution, there are many solutions. And we found out that the best possible solution is the one that the norm of X is minimum. Okay, the two norm of X is minimum. And when you solve this equation of minimizing the norm of X subject to the equation AX equal to B, you find a very nice result. You will find a very nice result where X star becomes equal to A transpose, A transpose. And here, for example, becomes A transpose inverse times B. This becomes the best possible solution in terms of the length of the vector X. Okay? So we have many solutions. I don't want to go further up here, but in any case, you have many solutions. Among all those vectors solution, you have X that has a minimum length. Okay? So that is described by these equations. Play an important role. Case number 3 is going to be a tall matrix. And again, if tall matrix X is equal to B, if B is an element of the range space of this matrix A, you have a solution. So you get some sort of a redundant equations to get rid of it, and it can be reduced either to this case, the previous case, or previous 2 cases if you have redundant equations. Either it's going to be a square or it's going to be a fat matrix. When B is an element of the range space of A, you have solution. However, in this case, I mentioned that in many applications, however, B is not an element of the range space of A, and therefore there is no solution for this equation. For that reason, people, they come up with this idea to say that, how about if I take B minus AX, call that one error, and solve a problem of optimization in terms of the minimization of this error. So you take this 2 norm of error. Now, obviously, 2 norm of error, you know how to write the 2 norm of error, right? Is going to be, when you minimize 2 norm of error, or a square of that, is going to be almost the same, right? So therefore, instead of taking a square root of, right, square root of, I take that B minus AX, which is E transpose, times E. So I try to minimize this E transpose E, right? E is a vector. So you multiply E times E transpose times E becomes a quantity. Then you minimize that. So how do we do this? You just write for this E, B minus AX transpose times B minus AX. It becomes an ugly expression in terms of the vectors B, A, and so forth, right? Yes? Oh, yeah, okay. Sorry about that. Thank you very much to mention this. Let me see. Is it better now? Okay. When you do this B minus AX, everybody understand what this means, right? E transpose E. If you have a vector, let me just write it down here so that you know. If I have a vector X, if I want to find the norm of the vector X, right? The norm of vector X is the square root of x1 squared plus x2 squared plus all the other terms, xn squared, right? But this expression here, if I take the 2 norm to the power 2, this one is going to be x1 squared plus all the other terms plus xn squared, right? But this expression can be written as x1, x2, all the way xn, as a row vector times a column vector, like that. Okay, so that means this becomes x, this becomes x transpose. So therefore, this quantity here can be represented as x times x transpose. I mean, x transpose times x. Sorry. Right? That's why I wrote E transpose E. For E, I can put B minus AX, transpose B minus X. You have to take the transpose of this quantity times this, take the derivative with respect to vectors and so on, and then when you do that, the outcome of the solution here becomes X star is equal to A transpose, A transpose. This times you have to take inverse of this times B. So the solution, therefore, becomes very similar to the other one, except that here you take A transpose times A inverse times A transpose times B. This plays an important role in data analysis and so on, as I mentioned to you before, okay? Because you collect a lot of data and you're trying to find the best possible solution. This equation is very important in one-dimensional, in image processing, two-dimensional image processing, three-dimensional image processing. We have an area within electrical and computer engineering. It's called DSP, digital signal processing. People work a lot on these equations in estimation and so on. Okay. So I just gave you some information about how the algebraic equation comes into the picture. Then other than this AX equal, by the way, there is an interpretation of this B element of the range space of A that it's not the case. Just imagine that you have two columns here. Call this one A1, call this one A2, just for sake of illustration. We have this matrix A times X, right, is equal to B. And we know that the B is not an element of the range space of A. What does that mean? It means that geometrically you can picture it this way, that A1 and A2 are two vectors, and let us consider these two vectors in, let's say, in a plane, okay, in three-dimensional case, right? So we have a plane like that, okay? Now, what happens is this, that A1 and A2, one of them lies here on this plane, here, A1 and A2, like this. You can imagine that, because the A1 and A2 can generate a plane in a three-dimensional space, right? So you take this, just imagine that these are components, they have each A1 and A2 has three components, okay? Now, when I say B is not an element of the range space of A, that means the vector B is outside of this plane. It's not lying in that plane, because if it was in that plane, would have been B element of the range space of A. That means you could just generate linear combination of that vector in terms of A1 and A2, right? But this is outside, so B is not an element of the range space of A. Geometrically, this means that the least square solution, we call it the least square solution. This is exactly this solution that I just described here. This is called the least square solution. Least square solution means that you draw projection of this B on this plane, so you find the projection point P. Is that clear? Now the projection point P is in the range space of A1 and A2. No, this is the geometric interpretation of that derivation that I just gave you here. Is that clear? Once you have B projected here, you find the projection point P, and that is something that you should be aware of from the analytical geometry that you learned, how to find the projection point and all these things. You know what I mean? Equation of plane, equation of like vectors in dot product and things like that. You know, so maybe I can, if I have time next time, I can bring some summary of those. Some of the important things about vector, and plane analysis. I can share it with you. But here is the geometric interpretation. So you do the projection, and then P becomes in the range space of A1 and A2, and that is exactly the outcome of that solution. That's the geometric interpretation. Now, you notice that one equation that is important here is AX equal to B, which is called the linear algebraic equation. I assume that all of you are, over this couple days that passes by, you have the opportunity to solve some of the problems that I assign, to review your mathematical stuff with the linear operator and all those examples that I solved similar to that. I assume that AX equal to B should be understood fairly well, okay? This is one type of equation that comes into the picture. The second type of equation that comes into the picture is AX equal lambda X. This equation is called eigenvalue eigenvector problem, okay? You guys that are working in the, you're in mechanical engineering department, right? All of you who have mechanical background, you know that if you take, for example, some mass spring system like that and so forth, and you solve some sort of a vibration problems, right? When you have a problem like that, the solution of that one, since you know that the vibration is going to be a sinusoidal type of solution, you substitute that, and then the end result becomes some equations of the form AX equal lambda X, okay? Where the modes of that oscillation basically can be obtained through the solution of this eigenvalue eigenvector problem, okay? So the reason I repeat that one here is that because when we go later on the control part of the course towards the end, we talk about the eigenvalues and so forth, assignment and all these things. So eigenvalues play an important role over there as well. Okay? I repeat that once more over there, but it is important that I talk about that right here because it has something to do with the algebraic equation as well. So this equation can be written as A minus lambda I times x equal to 0. Right? Because if I take the lambda x, by the way, this is called the eigenvalue. And this is called, both of them are called eigenvectors. Okay? Now, when you write this equation like this, it looks very similar to something that we discussed also. Let's call this one A tilde times x equal to 0. Oh my God, what is this equation? This is an algebraic equation, right? But it has a parameter lambda inside of it. Okay? It doesn't have constant terms, right? So there is a parameter lambda associated with this equation. Nevertheless, A tilde times x equal to 0, and because this matrix A is a square matrix, by the way, eigenvalue-eigenvector problem always gives you the matrix A that is a square. If you want to define something like eigenvalues for a non-square systems, that is a new, that it doesn't make sense to have that one, but you can develop theoretical results to talk about eigenvalues of a non-square matrices, for example. But that's something like there's a well, I don't know. Maybe you can define something crazy in future, okay? But in any case, in all the cases, A becomes a square matrix, okay, for the eigenvalue-eigenvector problem. So once you have A minus lambda I, you can consider A tilde. Now you have a homogeneous algebraic equation, correct? When do we have solution for homogeneous algebraic equation? Remember I mentioned something before. Let's go back here on this scrap paper. I put 2, 2, 1, 1 like that. If you have an equation like that, x1, x2 equal 0, 0, you know that the solution exists, right? So determinant must be equal to 0 in order to have a solution. If you have, for example, 2, 1, 1, 1 like that, there is no solution except trivial solution, right? For homogeneous algebraic equation, in order to have a solution, determinant of this matrix must be always equal to 0. So we go back here, we impose that the determinant of A tilde should be equal to 0. Right? So what does that mean? That means determinant of A minus lambda I must be equal to 0. Now, since determinant does not change, by changing the sign doesn't have any effect on the sign, right? Because if determinant of A minus lambda I is going to be the same as determinant of lambda I minus A, because you have a 0 on the right-hand side, you can multiply both sides by minus sign. It doesn't make that much of a difference. The reason that you write this one also in this convenient form like that is because of the fact that if you develop this expression, the highest order terms becomes positive instead of negative. Okay, so that is called, this equation here is called characteristic equation. When you develop this, we call this equation also delta of lambda, and that becomes equal to lambda to the power n plus alpha 1 lambda n minus 1 plus alpha 2 lambda n minus 2 plus da 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 plus alpha n. So you set this one equal to 0 to find lambda 1, lambda 2, lambda n. Those are called the eigenvalues of this system. Is that clear? So by solving this equation, you find this lambda 1 through lambda n. Is that clear? So once you find the eigenvalues, then you go back and say, well, I want to find out the eigenvectors corresponding to those eigenvalues, right? So how do we find that? You go back to that equation, A minus lambda I times x, right? So you write A minus lambda I times x. And then in this case, when lambda is already a value, you have a value for it. So for that lambda, you can put some values. Those values are lambda 1 through lambda n. So when you do that, maybe you can call this x now eigenvectors corresponding to the eigenvalue I. We call it v sub I equal to 0. Do you understand what I'm saying? So for each of those lambda, I equal 1 to n, you have this set of equations, which are actually homogeneous equation, all of them. Corresponding to each of these lambda 1 through lambda n, you can find the corresponding eigenvectors. Okay? Is that clear? Yes. Is that correct? Is that okay now? So you find the roots of this characteristic equation. You can call those lambda 1 through lambda n. You substitute back into that first equation that I showed you, a minus lambda I times vi equal to 0. Everybody understand why we put that I identity there, right? Because lambda is a scalar, I is a matrix that always helps you to make the dimension compatibility and so forth. So you have these eigenvalues and eigenvectors. Each of these equations gives you some eigenvectors. And then what is about this equation that is very interesting is that once you have v1, v2, vn, and so forth, you can combine them together. So we have lambda 1, lambda 2, lambda n, as I showed you there. Corresponding to this, you find v1 through this equation that I showed you, a minus lambda I times vi equal to 0 for all I equal 1 to n. So you solve these equations, and for each of those lambda 1 to lambda n, you get a set of vectors, v2, vn, like this. So we have a set of vectors, solution, right? And you know that the solution exists because the matrix A tilde for each of those eigenvalues gives you a square. It gives you a rank deficient matrix so that you have a solution. So the determinant of that matrix is always 0. So the solution exists. So you find v1 through vn. What is interesting about this is that if you take this v1, v2, vn, you put it in a matrix Q, okay, like this. v1, v2, vn. Since v1 through vn are a set of linearly independent vectors, they qualify as a basis in a particular vector space, right? So therefore, the matrix Q becomes non-singular. Is that clear? Now, if you take this set of vectors Q, and you have the matrix A, you take Q inverse AQ, you know what happens? If you multiply Q inverse with the A with the Q, you get a very interesting matrix, and that matrix is called the diagonal matrix. All the eigenvalues appear in the diagonal of the matrix A. Is that clear? Let's go through one quick example so that you can see the process. Okay? I take this example, A is equal to 0, 1, minus 2, minus 3. Okay, so that is a nice matrix that I like. Usually to take it in companion structure, which is good. So you take the determinant of lambda I minus A. You set it equal to 0. That becomes lambda squared plus 3 lambda plus 2 equal to 0. Is that clear? Everything? I could take any other matrix, but I had to calculate the eigenvalues through that lambda I minus A. Okay? So in order to write this equation, you should do this. Determinant of lambda times 1, 1, 0, 0, minus A, which is 0, 1, minus 2, minus 3, like that. So you can multiply lambda and then subtract it, and then you can do 2 by 2 matrix, right? That becomes lambda squared plus 3 lambda plus 2. The reason I wrote it very quickly is that this is a special matrix, which is called companion matrix. And it has a 0, 1 structure. If it is a 3 by 3, it becomes 0, 1, 0, 0, 0, 1. And then the coefficient here in the reverse order with the negative sign appears in this characteristic equation. It's so convenient. Okay? If you calculate this, you're going to get this equation. Okay? So now you find lambda 1 is equal minus 1, lambda 2 is equal minus 2, right? That becomes 2 eigenvalues. If you set it equal to 0, you get lambda 1 equal minus 1, lambda 2 equal minus 2. Right? Now, you go there and say, look, I have to take A minus lambda 1 times I times V1 equal to 0. Find out what happens in this case. If I do this, A minus lambda I, so let us put that one also. A is 0, 1, minus 2, minus 3. Minus lambda 1 is plus 1 with this negative sign, so it's plus identity 1, 1, 0, 0 times V1 equal to 0. So therefore, this equation here becomes equal to 1, 1, minus 2, V1 equal to 0. Aha! Determinant of this matrix is equal to 0, right? Sorry, determinant of this matrix is going to be 0. Therefore, the rank is going to be 1. Okay. The rank of this matrix is equal to 1. Determinant equal to 0. Therefore, the solution exists. The rank is 1. Therefore, you can find one linearly independent vector solution. Okay? Which one do you take that? Which one do you like to take that? So let's take 1. 1 and minus 1 is a good choice for V1, right? So I put for V1, 1 and minus 1. Everybody agrees? So we take the V1 to be 1 and minus 1. How about lambda A minus lambda 2 times I times V2 equal to 0? The other one is going to be minus 2, so it's going to be 2 here, 2 here. So that matrix becomes equal to 2 minus 1, 1, and what is here? Minus 2. Is that clear? That becomes A minus lambda 2 times I times V2 equal to 0. What would be the solution in this equation? One of the solutions that you can take as a linearly independent vector solution is going to be, let's say, 1 and minus 2, right? Now, as I promised before, these two vectors are two linearly independent vectors. They qualify as a basis. You can combine V1 and V2 together. Don't worry, I'm not going to go away from that. I show it to you here, right here. So Q becomes equal to V1, V2, which is going to be 1 minus 1, 1 minus 2, right? Now, believe me, if you take the Q inverse AQ, that becomes the matrix A hat, which has the diagonal element minus 1, minus 2, 0, 0. Is that clear? Yes? Now, the theory of eigenvalue, eigenvectors is very broad. Yes?
What's the point of A hat? What can it be used for? Just a place for the eigenvalues.
What is that? What
do you use A hat for?
Okay, very good. So let us, since you want to find out, we will get this example, for instance, where you have a system, okay, a dynamic systems. I didn't want to go to dynamic system right now, okay, but dynamic systems, when it's in motion, there are some modes of the system, okay? So if there is something which is called the state equation, which we will cover that one later on, but since you are excited to know right now, so the situation is that some dynamical systems are like this: x dot is equal to ax, plus BU, which we call that one state equation corresponding to a dynamical systems. It's a new notations, as you probably heard. How many of you heard about the state equations? Some of you. So any nth order differential equations can be written as a set of n first order differential equations, which are coupled, and those are called state equation. I'll give you the physical meaning of that one through the mechanical as well as the electrical one when we go to the control part of the course. But at this point, just assume that this system is there, and what happens is that if this matrix A is in diagonal form, if it is not in diagonal form, you can always find the diagonal form of it. You want to find out, let's say, the response of this system, assuming, let's say, that input is equal to 0, you have certain initial condition x of 0. Now, if this matrix is diagonal, like what I just described right now, like this, x dot becomes equal this times x, initial condition x of 0. Now, when you find the solution x1 of t, which is the first components of x dot, that becomes equal to e to the power minus t times x1 of 0. It means that you can find the solution of that state equations through the eigenvalues. Okay? Now, x2 of t becomes equal to e to the power minus 2t times x2 of 0. Because I gave you the initial condition of x of 0, you can find both x1 of t and x2 of t. Now, you said, where is the application? Well, this is the dynamic systems that you found, and it is very nice because this system is very stable. As time goes to infinity, both x1 of t and x2 of t go to 0. That means it dies out. It's stable. In many systems, mechanical systems, one of which, for example, an inverted pendulum in a cart, that's a good example for you guys to derive the equations of motions for inverted pendulum on a cart, right? You can write Newton laws and write the equations, or you can write through the energy equations. You can do that too. You can take the derivative of that one. It becomes again Newton laws. So you can find that one, right? Well, I'm talking about the Lagrangian, right? You know that, right? The Lagrangian, right? Kinetic plus potential energy and solvents. So what in most cases, like in that problem, the problem is gives you, if you find the response of that system after you model it, it's going to be an unstable system. Okay? So the goal of control system is to stabilize it. So sometimes you want to shift those eigenvalues to a desired location in order to stabilize it. That means you want to improve the performance and so forth. Is that clear? Did I give you the enough answer to that question? So those eigenvalues play important role in the motion characteristics of the systems. If the system is unstable, you want to stabilize it. Is that clear? If the system is stable, again, you want to improve the performance. Okay? You will see that for a manipulator, 2 links manipulator or 3 links manipulator, when you write the equations of that, it's going to be a vector matrix equation, which looks very ugly. We will derive that one towards the end of the course, right? So that equations is a vector matrix equations, which you probably did not see before, right? So that equation plays an important role because based on that equation, we want to find out what kind of a control you have to apply in order to improve the performance of that manipulator. For example, sometimes you want to achieve certain goals in a fast way, so you have to improve the performance, right? So that is where those eigenvalues are coming into the picture. Is that clear, more or less? Okay, I don't want to talk too much more about that. So whatever I cover here, somehow you will see that. Not that we just say it and we don't use it. You know what I mean? We will use it. Okay. Now, the theory of eigenvalue, eigenvector is very broad. I just gave you one example to show you that if you have distinct eigenvalues, you get distinct eigenvectors. That means linearly independent vectors. It can happen that there are some repeated eigenvalues, and the solution goes to some sort of a Jordan form, and that is beyond the scope of this course. Okay, we don't want to talk about the Jordan form and all these things. Okay, so that is more mathematical analysis. I just wanted to show you a little bit of a flavor of this second equations, other than algebraic equation, the concept of eigenvalue, eigenvector. Is that clear? Okay, so now, what did I want to say? Oh, there is another topic which is, I will cover that one a little bit later, that has something to do with the solution of these equations, which I don't think that it is necessary right now to talk about it. And that is called, it's called a function of matrices, okay? How many of you heard about function of a matrix? I know you. Nobody heard about that, right? Nothing? Let me just excite them a little bit. Huh? Okay. So let us excite you about that part. But I'm not going to cover too much about it. Later on, I have to repeat that one for dynamic system. What is a function of a matrix? Let's say, for example, I have something like this. E to the power A like that. This is called a function of a scalar. You're all familiar with it, right? If I write f of a, but put also e to the power at like this, I can call this function of a parameter a rather than t, because maybe t you can consider as a dummy variable, dummy quantity. Another one, f of a equal to a to the power k, right? You're familiar with that too. That means a multiplies k times. Let us take another one. F of a is equal to sine of a, right? That is also familiar to all of you, right? Mathematician at some point, they said, okay, let us see whether we can do something more than that. Let us define something like this. F of a is equal to e to the power a. What? Let us call this one f of a matrix A, call it e to the power at. What? A matrix exponential to the power of matrix? I have never seen that before. Okay. Another one. This one, let's take this one. F of A is equal to sine of a matrix. Oh my God, what is the sine of a matrix A? Right? Lots of things come into the picture. Here, for this one, f of a becomes a to the power k. Among all these functions, these are called function of matrices. Okay? This is called function of a matrix. Among all of those, there is one function that makes sense to all of you. Which one is that? Huh? What is? Huh? Very good. This one. Because it says that you multiply a k times and you get this value. Right? Now I tell you immediately something very interesting. Suppose I have, you know that e to the power x is equal to 1 plus x over 1 factorial plus x2 to 2 factorial plus da 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 da. This is the power series expansion for e to the power x. If I have e to the power a, can I write that one as I plus a over 1 factorial plus a squared over 2 factorial plus da 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 da? Yes? Now this one is to the power 2. I could understand this. I could understand all the others. So therefore, e to the power a exists. Is that clear? Yes? Makes sense? Now you say, okay, something that you didn't even believe that function of a matrix exists, now you open your eyes and say, my God, this makes sense. The same thing with sine function, cosine function. Remember, sine function x over 1 factor plus x minus x cubed divided by 3 factor. Remember the power series expansion of all those functions from one of the courses that you took in trigonometric or something like that. I don't know. Power series. Okay? So that makes sense, right? Oh, no, there is a theory behind that, for example, if you want to find, for example, a to the power 100, right? And my friend over said that you multiply a 100 times. Would you do that? You will never do that. So there were two people, mathematicians. One of them was called Cayley. The other one was called Hamilton. Okay? I'm just giving you the historical background. So Cayley and Hamilton. Cayley was very good in matrix algebra, matrix analysis. Hamilton was very good in function. Now here we go. Function of a matrix. That doesn't mean that Hamilton was not good in matrix theory. But this guy was more involved in matrix theory. This guy was in function theory. Together, on a very nice sunny day, sat down under a tree, and they say, "Well, let's solve the problem of function of a matrix." And they were able to solve this problem much faster, much quicker. Okay? Beautiful theory. Okay? So when it comes to the point of talking about this, I'll talk about it. Is that clear? So, why is this important, Cayley Hamilton? Is because the solution of that equations of dynamic systems has something to do with e to the power 80. But let's talk about that when the time comes. Since you were really excited, that lady over there asked, what is the eigenvalues and so forth, I had to change my direction. Did I make you happy, all of you? Yes? Huh? No? Okay. So when I make you happy, I need a smile on your faces. Okay. Good. Okay. So now let us do the following. Today I'm going to start talking about something which is interesting. We just start on that, and it's called homogeneous transformation. So let's talk about that one a little bit. Let's see whether I have here something. I will probably derive this one, so I don't want to mix up these things. Okay. I call this one, is it clear over there? Kinematic. One, I call it geometry. That is the topic that I'm going to start right now. I call it kinematic 1, geometry. Today we talk about the position and orientation of a rigid body. Okay? First, I will go through this material through my own way of handwriting. I mean, the way that I wrote it before. And then I will also refer to the textbook and see, because this way is easier to understand at this point. But later on, I go exactly the notation of John Craig. By the way, everybody saw the book of John Craig. How many of you purchased the book? You purchased the book or no? It's a good book. If you want to get involved with robotic stuff, that is one of the best books available. Okay. So Craig's book, John Craig has a very peculiar notation when he wants to write this transformation matrices, he put the matrix transformation matrix, and then there are two elements on the left-hand side, up and down. So it's going to be a little bit difficult to understand. If I put that one on lecture notes, you get confused, because when I put these matrices together, it's really confusing. Okay? So not to worry, I will make you familiar with that notation once you get used to understand the basic concept of homogeneous transformation and what is the matrix representation of that and so on. Okay? So let's do that. I draw this picture. Let me, instead of, how about if I also make copies of this and give it to you? It's not a bad idea. I give this one also to you. Okay, let me just show you, and then I repeat that one here as well. Not to worry, you don't have to write right now immediately. So you can first understand what I wrote here. It goes too much. Okay. Is it readable? Huh? So position and orientation of a rigid body. That's why I don't want to write all of this, because it's going to be very boring. I write it, but then after that I show you only through the pictures in a separate page what happens with the derivation. Okay? So let us take a look at this. I wrote here, let O-XYZ be a coordinate frame fixed to the ground, like this one. Okay? Then the position of the rigid body, point O prime, okay, is represented by, I put x0, y0, z0. This x0, as you can see here, is a boldface notation of x. Okay? So the first component of that one becomes x0 without boldface, y0, z0. Is that clear? When you get my notes, you will understand, obviously. It's natural. To represent the orientation, because the body that you have, it has always a position and some sort of orientation. You have to have both of them intact. Is that clear? So to represent the orientation of the rigid body, three coordinate axes I put here like that: xb, yb, and zb. Can you see that? If it is not feasible for those people back there, people over there, can you see that, or should I magnify it? Everything clear? Okay, so good. So you have this xb, yb, and zb coordinate system on the rigid body. Now, attached to the rigid body, which form another coordinate frame, which I call it O prime, xb, yb, and zb. That's clear notation, right? Now, along this xb, yb, and zb, I put three vectors. Those three vectors could be E1, E2, E3. I call it N, T, and B. Anybody has against that notation? No. You can call it anything you like. So that is N, T, and B. Okay? So now I take these three vectors, okay, and generate a matrix which I call it R. The R matrix consists of three column vectors, N, T, and B. Now, as you can see, all these three vectors are mutually orthogonal to each other. That's obvious too. Everybody understand that? Now, what does that mean? Mathematically, it means that N transpose times T is equal to 0, T transpose times B is equal to 0, B transpose times N is equal to 0. That is called the orthogonality of the two vectors. Is that clear? Okay. Now, since they are unit vectors, the magnitude of each of them would be also 1. Okay? Now, the matrix R has a special name in matrix algebra. By the way, there is also, when I talked about the matrices over there, one of them you learned, I talked about that when you asked me, is a diagonal form. So there are other matrices which are called companion matrices. Some of them are symmetric matrices, okay? Some of them are called orthogonal matrices, okay? This matrix R has a special name too. It's called orthogonal matrix because the transpose of that matrix becomes the same as its inverse. It's not only the one unity, I mean, the identity matrix is a perfect orthogonal matrix, right? But that is not the only one. You have a lot of other matrices that have orthogonal properties. So that means the transpose of those matrices are the inverse of that matrices. Is that clear? In fact, it's very interesting that this orthogonal, look, let's just quickly go jump in something else, okay? To excite you also, since you're interested. Maybe I'm interested. You're not interested. I don't know. Anyway, look at this. If I give you an algebraic equation Ax equal to b, right? And this matrix is orthogonal, what happens? The inverse of that matrix is the transpose, right? Isn't that wonderful that you take, instead of inverse of a matrix, you transpose it? Now, in numerical analysis, inverting a matrix is a little bit tricky. You don't want it to take the inverse of a matrix the way that you think it should be. They never do that inverse the way that you just do it analytically. You know how to take the inverse of a matrix. You just take the matrix of, you do that matrix of adjoint divided by determinant, right? That is the way that you do the inverse matrix calculation, right? But if A is orthogonal, X becomes A transpose times B. Then you say, people in mathematical domain, there is an area which is also very nice. It's called numerical analysis. Beautiful area too, okay? So what happens is that they do something which is called orthogonal factorization. So this A matrix can be divided as a Q times R, where Q is an orthogonal matrix and R is an upper or lower triangular matrix. So transferring this matrix to this product QR is a very long process. You have to go through the orthogonalization process of a Schmidt, another mathematician. Now, you say, hey, I take the inverse of matrix very easily like that myself. Why should I go through this? But from a numerical analysis point of view, you have to pay the price. The algorithm looks like this, 1,000 lines. But when it computes in a numerically reliable fashion. Do you understand what I'm talking about? So that is why, for example, this Q becomes orthogonal, this R becomes upper triangular matrix and so forth. Then you reduce the problem after that to something that basically takes the transpose of a matrix, and then the back substitution can be obtained through the upper triangular matrix of R and so on. So I don't want to talk about that. I just wanted to show you that there is certain advantages of those kind of matrices also. Is that clear? Yes. So why do I make it black here? Okay. Well, so that is why R transpose R inverse here has the property that R transpose times R becomes identity because inverse times R becomes identity. So very nice. So this is a summary of what I just discussed. Now, let us do the following coordinate transformation. Is everything there? No. Coordinate transformation. Oh, it's almost 1 hour. This takes half an hour to explain. I don't want to go very quick, okay? So as I promised, I had a 1 hour lecture, and you have a long weekend too. I give you the homework, so is that acceptable? Thank you very much. So sorry that I gave you a headache if I gave, with all those mathematical stuff. It's a good point to stop. So remind me about coordinate transformation.